Hello. Good afternoon, dear participants. Welcome to Parallel Programming with Cuda training. Today is the second day of this training, and Dr. Ozcan Dulger will continue his presentation today. We cannot pay attention to these issues. We cannot unmute participants, and we cannot turn on your microphones and take loud questions. So please do not type your questions into the chat box. Just you can submit your questions in Q&A box. Dr. Ozcan Dulger, I ask you to begin your presentation. Thank you.
Thank you so much, dear Saide. Hello, everyone. Today is the second day of our Cuda training. My name is Ozcan Dulger. I am visiting assistant professor doctor at the Department of Computer Engineering in Middle East Technical University, and also is an assistant professor doctor at the Department of Computer Engineering in Artvin Çoruh University. Let's start the issues in the second day of our training. In today, I will show you two common problems on the GPU. One of them is about the non-coalesced access to the global memory. The second one is about the warp divergence problem. Then I will show you the CUDA streams and multi-GPU approach in CUDA programming. And at the end of the lecture, I will show you an example about the vector addition by using streams. And we will overlap the instructions of the vector addition and run in parallel by using CUDA streams. Let's start with the first issue. It is the coalesced access to the global memory. And the read-write operations on the global memory of the GPU perform segment by segment. That means when a thread tries to read a value from the global memory, first the segments that the data belongs to are given to the threads or verbs, then thread read that value from segment. Remember that the threads in a verb are physically related to each other. So in order that the verb completes execution of the instruction, all the threads in the verb must complete execution of the instruction. So in this problem, in global memory operations, if the threads in the verb access to the different segments of the memory, the read operations become serial. This is an illustration of this problem. The rectangles at the bottom are related to the verbs, and the rectangles at the top are related to segments of the global memory, and the arrows are related to the threads in the verb. Here, as you see that the threads in a verb are access to the different segments of the memory, as you see that. So these operations become serial, and the execution time affects adversely because of this approach. So how can we solve this problem? If we force the threads in the verb access to the same segment, we can overcome this problem. So all of the read operations will take only one transaction. As you see that the threads in the verb access to the same segment. I would like to show you an example here about this one. Sorry. Okay, let's continue here. We have a two kernel here, which is about non-wireless access problem. The first kernel is related to the wireless access to the global memory. We call it full wireless access. Why? Because all the threads in the world access to the same segment of the global memory. How we can ensure this one? By using global thread IDs of the threads here. The threads in the world here access to the same segments. When reading A, when reading B, and the for loop takes 100 iteration. So there will be 100 read operations for A and 100 read operations for B, but all of them are fully coalesced. So the load operations of A or B will take one transaction. In the second Cuda kernel, we use a random generator here inside for loop. So we obtain a random value, random index value, and for a thread here, for each thread, we obtain a random index value, and the threads in the work try to access to the this random location on the global memory. So the threads in the works may access to the different segments of the global memory. In the worst case, all of the threads in the world access to the distinct segments, different segments of the global memory. So the world access to the 32 different segments. That means load operations of A and load operations of B will take at most 32 transactions in this kernel. And we use XOR wow generator, which is a library in the Cuda for random number generators. And we use Cuda event record to measure the execution time of the kernels. Okay. Okay, let's and we run these kernels on the GPU and measure the performance by using CUDA profiler. There are some metrics about this wireless access to the global memory. The first one is about GLD transaction metrics. This gives us the number of global memory load transactions, the total number of global memory load transactions in the kernel. And the second metric is about the average number of global memory load transactions performed for each global memory load. So we count the number of load transactions in each global memory load, and we get the average of them. This is the second metric, which is called GLD transactions per request. Okay, before showing the results of profiler, let's look at the execution times. The execution time of full wireless access. By the way, the number of data is 32,768 here, and the execution time of full wireless access kernel is around 0.001 seconds, and the execution time of non-wireless access, the second kernel, is this 0.0016 seconds. So the speed up obtained by the full wireless access is about 14x. So we achieve 14x speed up with full wireless access. Let's examine the results of profiler. First, let's check the results of full wireless access. The first metric is the total number of global load transactions, which is here 204,800. And the second one is about the average of the global load transactions, which is 1 as we expected, because all of the global load operations in all of the verbs and in all of the threads take exactly 1. So the average is exactly equal to the 1 in full quality access. And the total number of global load transactions, how we can calculate the total number of global load transactions, I would like to show you here with calculator. So the number of transactions is related to the verb. So at first we need to calculate the number of verbs on the kernel. Here the data size is 32,768. Sorry. Yes. Okay. In order to obtain the number of verbs here, we must divide it to the number of data in the verb, the number of threads in the verb, that is 32. Sorry. Let's divide it to 32. Here we have 1024 verbs, and here at each verb, how many transactions are taken? One for read A, one for read B, and when we multiply it with 100, for each thread, 200 transactions are taken. So since the verb has 32 threads, we must multiply the number of verbs with the number of threads and with the load transaction, total load transaction of each thread, which is 200. And as you see that we get, sorry, I made a mistake. We have, sorry, not, I shouldn't consider the number of threads. I'm sorry, just consider the verb. We have 124 verbs, and for each verb, not thread, for each verb, this for loop takes 200 transactions because this is fully coalesced access. All the threads are accessed fully coalesced. So the total number of transactions of the verb will be 200. I'm sorry. So when we multiply the number of verbs with the total number of transactions of a verb, we get this value, which is here 204,800, as you see. Okay, and okay, let's check the result of the non-coalesced access kernel. I will not calculate the total number of global load transactions. We can do it with that formula. And we get the number of load transactions per request is around 30, as you see. And I told you that the number of transactions will be taken at most 32 transactions. So 30.6 is very close to the 32. So we got the correct results from the provider. Let's extend the data size here by setting it to 22. Now the data size is over 22, and the execution time of full wireless access kernel is around 0.009, and the execution time of non-wireless access kernel is 0.5. So the speed up is around 52x, as you see. And when we again check the results of provider, the global load transactions per request is again exactly equal to the 1, because all of the threads access to the same segments in all works. Again, the global load transaction per request for non-wireless access kernel is around 31. It is very close to the 32. So we obtain a proper results from the provider. So this improvement is very important. But not all of the problems can be solved with full wireless access or non-wireless access. Maybe we need some trade-off. We need a trade-off between full wireless access and non-wireless access. So how we can assure that trade-off? We can use grouping. We can group the number of consecutive segments. Here, each group consists of consecutive real segments, and the number of segments in these groups can be between 1 and data size divided by 32. 32 is the number of elements in the segment. So the number of segments in a group at most data size divided by 32. That is all of the segments consist of in a single group, or it may be one segment for each group. So we will have many groups in that case. So we can use the same idea in the previous slides. Now we are trying to force the threads in the work to access to the same group, not access to the same segment. Now we are trying to force the threads in the group of work to access same group here. So we can modify our code with grouping idea. Here there's an example about it. Let's examine this example. We create a semi-wireless access kernel, and we set the number of segments in a group at the beginning, and then we are taking a random index within this group. Within this group, that means we can access to the segments consist in the given group. So we are trying to read the value from the given group, and we take here a random number within this group, and we try to read A and B within this group. In this example, there are 16 segments in a group. We set the number of segments in a group as 16. So that means the load operations in A and in B take at most 16 transactions, because we have 16 consecutive segments in the group. And there are parameters here. The segment size is 128. This is in terms of bytes. So the number of data in a segment is 32. And the second parameter is group size. That means the number of data in the group. Here's the number of data in a segment is 32, segment size divided by 4. And we multiply it with 16. 16 means the group consists of 16 consecutive segments. So then we have a group count parameter, which gives us the number of groups here. The number of groups we obtain it by dividing data size to the group size. And we obtain the number of groups here. So in here, when reading A and B, the load operation take at most 16 transactions. If you set this one as 1, so that means all the groups consist of a single segment. So this is equal to the non-coalesced access kernel. If you set it to the group count, only one group is created and it consists of whole consecutive segments. So in that case, this is equal to the non-coalesced access kernel. I'm sorry, the second case. Now, if you set it as the group count, this is equal to the non-coalesced access kernel. If you set it to the 1, this is equal to the full coalesced kernel. So this number enable us to obtain a trade-off between fully coalesced and non-coalesced access. And in this example, the load operations take at most 16 transactions. Let's check the results of profiler and the execution time. Now the execution time of semi-coalesced access is 0.0074 for the data size is equal to 32,768, and we obtain around 7x speed up with our semi-coalesced kernel. And when we check the profiler result of a semi-coalesced kernel, here we obtain 13.4 global load transactions in average. So this is also very close to the 16. So we can consider that we obtain a true solution results with profiler. When we extend the data size to the 2/22, now we obtain 22x speed up with semi-coalesced access. Still, it is a good result for us when we compare it with the non-coalesced access. And when we check the global load transactions per request, it is around 13.4. So this is also very close to the 16. So we obtain a proper result from the provider. Okay, let's continue with the next problem. The warp divergence. A warp executes if-else structures as single instruction. So if-else structure considered a single instruction for a verb and it executes at the same time. But when all the threads in the verb complete execution of if-else instructions, the verb completes the execution of if-else instructions because the threads in the verb are physically related to each other. Sorry.
Dear participants, we have a technical problem with PC. Please wait to solve this problem. We will come back soon.